In this lecture, we will talk about the variance and standard deviation, the concept of it and how we calculate it. In the previous lecture, we discussed about the mean and we saw that for what purpose we basically use the mean. So the basic idea about the mean was to find the one representative for the whole data set. Let's take this example again. If I want to find the mean of the data set for which x is 1, 2, 3, 4, 5, 6, then the mean that we get over here is basically, it is after doing some calculations, we get the mean which is 1 plus 2 plus 3 plus 4 plus 5 plus 6, and then divided by 6, we get 3.5. So the mean is 3.5. Now it's quite apparent. It is nothing to be explained about over here. It's quite observable that if I say that the mean of this data set is 3.5, then if I ask you the question that is it a good representative of my data set, what will be your answer? And how would you come to the answer? When we say that one thing is representing the other, then this is only possible when both are the same. Mathematically, this means that if one thing is representing the other, then the difference or subtraction between the two should be equal to 0. Like for example, if I have a shirt of some shade of red and I want to have a similar red shade, then I would go to the market taking the piece of cloth that I have got, and I will try to match that shade of red that I have got with the different shades of red which the salesperson basically shows to me. And I will pick up that red color which will match with the one that I have already got. That is the difference between the two should be 0. So if I ask you that whether 3.5 is a representative, a good representative of my data set, then I would say no, because I can see this thing that every single value in the data set is different from 3.5. The one which is closer to it will show some better representation, but all the other values which are away from 3.5 shows that 3.5 is not representing them properly, which basically means what? This means that the prediction that I had made using the mean which is 3.5 is not a very good prediction, rather it has got errors. And as a data analyst, just like it is important to model the data and we did it in the form of the mean value model, it is rather more important, I would say, to find the errors in the model. And these errors are basically called the variances and standard deviation. And for the mean value model, these are the variances and standard deviations for the mean value model. Now, instead of just jumping onto the formula, how should this error be calculated? If I say this error, sorry, if I want to find the error, then basically the idea should be that I should find the difference between the value and the mean value. So 1 minus 3.5, I should be able to find this thing. This would give me that how far 3.5 is away from the value which was 1 in the data set. I should be able to find 2 minus 3.5. This would give me that the distance between 2 and 3.5, that is how much far 2 is from the mean, which was the expectation. 3 minus 3.5, and definitely this would be closer to 3.5 because 3 is much closer to 3.5 as compared to 1, 2. I should be able to find 4 minus 3.5, and likewise I should be able to find 5 minus 3.5, and so 6 minus 3.5. Now all these numbers must be able to be connected in some way or the other. So these are the individual errors. We should, in order to find the total error, we must be able to add them to find the sum of the errors, to find the total errors that we have got. But there's a big problem over here. The problem is this, that if I take 2 minus 3.5, then whatever the result is, it will be a negative value. And if I take 3.5 minus 2, it will be the same magnitude but a positive value, for example. And this will be the case for every other value. And there's also a possibility that in some data set, it might be so that, and it is happening over here, that half of the values are same as the other half, but with the opposite sign. And when we add them together, we get a value which is 0. Like for example, if we do this thing over here, then 1 minus 3.5 is minus 2.5. So if we run this calculation, then this would go something like this. It is minus 2.5 plus 1.5, sorry, minus 1.5, and then minus 0.5. 3 minus 3.5 is minus 0.5, and then plus 0.5, and then plus, so it's 1.5, and then plus is 2.5. So see, if I add them all, I get a value which is 0, and this would be interpreted as that the net error is 0. But we can see this thing that the net error is not 0, because every individual value in the data set, when subtracted from the mean, was not giving me the result 0. So this means these two things must be rectified. The first one, that whether the value of the data set or the mean should be taken first in the subtraction, and how to circumvent, how to avoid this 0 result. So there are two ways to do it. The first one is this, that do not consider the signs, just take the magnitudes. And the second one, which is the more, which is preferred over the first one, is to take the square of the values. So rather doing it in this way, it is better that if I take the square of the values, then this would resolve both the issues. The first one was that which value should be taken first, because whatever the value is, whichever value is taken first, the sign problem would be solved as we are taking the squares. And the second issue, that was, in this case, the net result would not be 0. So now, since we are taking the square of the things, then definitely this would not be the results now. Rather, minus 2.5 square would give me something like this, 2.5 multiplied by 2.5, and this is 6.25. It's a pure positive value. So 6.25, and likewise 1.5 square gives me a result which is 2.25. So this is 2.25, and there will be a plus sign now. Then this is 0.5. This was minus 0.5, so minus 0.5 square makes it equals to plus 0.25, and then again plus 0.25. Then again we have got 2.25, and then we have got 6.25. And when we sum them all, so it's basically 6.25 plus 2.25 plus 0.25, then multiplying by 2 is 17.5. So the error, not rather error, rather, since we have taken the squares, so it's 17.5. 5. So this means that now the sign problem is solved, and because of which the two issues are also resolved. But still the calculation is lacking something. Whatever we have calculated is not the error, it's basically the square of the errors. So it's error square thing. But this error square thing is still lacking something. We know that every individual value has a certain, every individual value in the data set has a certain percentage or certain weightage of occurrence. And that weightage should be included in the calculations because it is the percentage amount by which it has the potential to come at the output. So all these, since it was an ungrouped data statistics, so all of them had a weightage which was basically 1 by 6. So multiplying this result, by 1 by 6, or dividing all the things with 1 by 6, so 17.5 divided by 6 is divided by 6 and multiplied by 1 by 6. So please note this thing. And I can do it in this way because 1 upon 6 would appear as a common for every value, so we can do it in this way. So 17.5 divided by 6 gives 2.91. So this normalizing factor has played its role, 2.91. This thing that we have just calculated is basically called the error square, and the error square term in statistics is called the variance. So this is the same thing as the variance, right? But since we are rather interested in the error term instead of the error square, so by definition in mathematics, if we have a square on something and we take the square root of it, this gives the standard deviation or the error term, or this gives the reduces the power to 1. So square root of this variance gives the standard deviation, and in this case, for this simple example, the square root of 2.91, the power of zero point 0.5, is 1.7078. So the standard deviation for this simple data set is equals to 1.7078. So this is the standard deviation and the variance concept. If we apply the same thing to the available data set that we have got, just to call this thing that we were working on this data set. So this was the data set that we were working upon with x these values, and if you find we just found the mean of it, which was 3.5, and the variance, sorry, the mean of it, which was basically 134, and if you find the variance of it using the same idea, if you find the variance of it and then later on the standard deviation, so the variance comes out to be 100.4708 and the standard deviation is 10.02, right? So we have got three things now: the mean value, the variance, which is the error square term, and the standard deviation. Now, what we do with it? The last thing in the analysis that we were discussing, it was about the prediction. What do we predict? Now remember this thing that in statistics, whenever we do the predictions are equal to the statistical model that we have got plus minus the error term in the statistical model. Now the statistical model that we have used in this example is the mean value model. And the error of this mean value model was indicated by the standard deviation with this Greek symbol sigma, and the variance is basically sigma square. So mu plus minus sigma, in our case 134 plus minus 10.02, and when we do these calculations we get 123.98 for 134 minus 10.02, and when we sum 134 with 10.02 we get 144.02. So this means that for the given data set, what we can predict is that if this experiment is performed again in future, the error margin is from 123.98 to 144.02. That means the predicted value would be anywhere between 123.98 to 144.02. So that's how we do these predictions. This is the simplest available prediction that could be done on an ungrouped data statistics using the mean value model. So this was about the ungrouped data statistics, and the next lecture we would see that how we perform the group data statistics and the frequency distributions. In this example, there was no use of finding the frequency distributions. Why? Because as we discussed earlier, every individual value has the same frequency of occurrence, which is 1. But in group data statistics, this frequency value changes, and there we would also see that how we find the frequency distributions. So thank you very much for this lecture. Any questions you can ask me using the comments or contact me. Thank you very much.